The kinetics of a chemical reaction is defined as the rate at which an amount of reactant is converted to products per unit time. Considering the rate of change of the concentration of reactant A with respect to time, which is a change in concentration of the reactant on a change in time, where A0 is the initial concentration of reactant A at time t0, while the rate of the reaction is equal to the rate at which the reactant is consumed on the stoichiometric coefficient, and a negative sign indicates that the reactant is being consumed. So the concentration of the reactant is dropping from the initial concentration. And similarly for reactant B, we have the rate of change of the concentration of reactant B with respect to time on the stoichiometric coefficient, and that's equal to the rate at which the product is formed on the stoichiometric coefficient. And the unit of the rate of the reaction is in molar per second, or moles per litre per second. Several factors can increase the rate of a reaction, and one of those is the concentration of a reactant. So for example, if the concentration of hydrochloric acid in this reaction increases in an aqueous solution, then more collisions between these hydronium ions are going to occur with the aluminium solid bar. Now another factor is temperature. So an increase in temperature causes more collisions between the molecules and the aluminium solid. And another factor is surface area. So if you break the aluminium bar into two, then you have more aluminium atoms on the different sides of these bars that can collide with the hydronium ions. And catalysts can also increase the rate of the reaction, which we'll look at in more detail. But basically, catalysts do not participate in a reaction. They just increase the rate of a reaction by decreasing the activation energy, which is the energy required to initiate the reaction. And other environmental factors, such as pressure, phase changes, and so on, can influence the rate of the reaction. Ammonia decomposes at the following rate, and we're asked to find the rate of production of nitrogen and hydrogen gas. Well, first we need to make sure that this reaction is balanced, and then we can write the rate of the reaction using the stoichiometric coefficients. So we have the rate of decomposition of ammonia and the rate of production of the gas products. And now if you substitute for the given quantity of the rate of decomposition of ammonia and negative because the reactant is being consumed, then you can solve for the rates of production of both gases. Now if the initial concentration of ammonia is 0.024 molar, what is the concentration after 1.5 seconds? So we have the change in concentration of ammonia over time is equal to the concentration of ammonia at 1.5 seconds minus the initial concentration, which is given, and that's divided by the change in time. And we have the rate of decomposition given in the problem, so you can solve for the concentration of ammonia at 1.5 seconds. We can use experimental methods like spectrophotometry to monitor the concentration of reactants and products to determine the rate of a reaction. Now the rate law expresses the rate of reaction as proportional to the concentration of each reactant raised to a power, and each power is the order of the reaction with respect to the reactant, and the sum of the powers is the overall order of the reaction. Now the constant of proportionality K is the rate constant, and generally this is temperature dependent, and the units reflect the overall order of the reaction. We can determine the order of a reaction with respect to each reactant by conducting different experiments where we measure the different initial reaction rates using different initial concentrations of the reactants. So for example, if we want to determine the order of a reaction with respect to reactant A, well, we'll look for the experiments where the concentration of the other reactants is constant, and now writing the rate law for experiment 4 and dividing this by the rate law for experiment 3, then cancelling out the terms for reactant B and C, and then substituting for the rates and the concentrations of reactant A, where we can take the quotient to the power of x, and the order of the reaction with respect to reactant A is 2. And if you follow the same process, you'll obtain y equals 1 and z equals 0. And a number to the power of 0 is simply 1. And therefore the order of the reaction is the sum of the exponents, and the unit for the rate constant can be obtained using dimensional analysis. The following experimental data was obtained for finding the rate of the following reaction. And part A asked to write the rate law, which we can write in the following form. So using experiments 1 and 2, where the concentration of B is constant, we can find the exponent for reactant A by dividing the rate laws obtained from both experiments. So x is equal to 2, and I'll leave it for you to select two experiments to verify that the order of the reaction with respect to reactant B is 1. Now if half of reactant B is consumed in experiment 3, what is the remaining concentration of A? So 2 moles of A are consumed for every mole of B. And if half of reactant B is consumed, assuming you have the same volume of both reactants, so therefore the remaining concentration of A, and calculate the value of the rate constant, we can use any experiment. So substituting the values from experiment 1 into the rate law, you'll obtain the following result using one significant figure. We can use the previous equations that were derived for the rate law to find the relationship for the concentration as a function of time. So here we wrote the rate at which reactant A is being consumed, and if the order of the rate law with respect to reactant A is 0, so we have the rate constant multiplied by the concentration of A raised to the 0 on the right hand side. And this here is equal to 1. And we can write the change in concentration on the change in time as the concentration at time t minus the initial concentration at time 0 over time t minus time 0, which will take at t equals 0. And multiplying through by t, and then adding the initial concentration to both sides. Therefore the concentration of reactant A as a function of time is a linear relationship, with the slope being the negative of the stoichiometric coefficient by the rate constant, and plus the y-intercept at time 0. If a reaction is first order with respect to a reactant that we're monitoring, we can write the following relationship using the definitions for the rate law that we derived earlier. And we have the concentration of reactant A here to the first power. Now to obtain a relationship between the concentration of the reactant versus time, then we need to do calculus, where we'd write the derivative of the concentration of A with respect to time, and then solve this first order differential equation. But that's beyond the scope of this course, so I'll just write the result that you'd obtain if you solve the ordinary differential equation. So we'd have the natural log of the concentration at time t is equal to the natural log of the concentration at time 0 minus the stoichiometric coefficient by the rate constant by time. And if we use a semi-log plot, we'd obtain a linear relationship between the natural log of the concentration at time t with respect to time t. And the slope of this straight line is the negative of the stoichiometric coefficient by the rate constant, with the y-intercept of the natural log of the initial concentration. For a second order reaction, with respect to the reactant being monitored, we have the following ordinary differential equation using the relationships for the rate law that we derived earlier. So here we can see that the concentration of reactant A is raised to the power 2. And if you solve this ordinary differential equation, which is beyond the scope of this course, you can obtain the following relationship. So here the relationship between the reciprocal of the concentration of reactant A at time t and time t is linear, with the slope being the stoichiometric coefficient multiplied by the rate constant. So here we can see that because the reactant is being consumed, then the concentration at time t is going to keep getting smaller than the concentration at time 0. And therefore the reciprocal becomes larger, and that's how we have a positive slope. The half-life is a critical parameter that applies to first order reactions. So recall that the relationship that we derived earlier, we can do a bit of algebra by subtracting the concentration at time 0 from both sides, and then applying the log rules, and taking e to the power of both sides, and then multiplying by the concentration at time 0, we obtain the following relationship. And for the special case where the stoichiometric coefficient is 1, so therefore the concentration of the reactant decays exponentially from an initial concentration at time 0. Now the half-life is the time taken for half a substance to react, so we can set the concentration at time t to be half the initial concentration. Then doing some algebra, you'll obtain the following relationship, where the natural log of 2 is around 0.693. So as we can see, the half-life is constant for a first order reaction because the initial concentration keeps dropping by half. And the half-life only depends on the rate constant, so therefore for a higher rate of reaction, you get a shorter half-life. We can apply the kinetics of first order reactions to radioactive decay. So in this example, a nucleus of radon-222 decays into polonium, and an alpha particle, or a helium, is shed from the nucleus of radon. So this radioactive decay can be modeled using a first order differential equation, which is similar to the differential equation for a first order reaction, where we derived the half-life. Now the solution to this differential equation is as follows, where the current number of nuclei is equal to the initial number of nuclei by e to the power of negative lambda t, where lambda is the rate of decay. And the half-life, now if we plot this solution in terms of the percentage of the mass of radon-222 left over, and you can see that 50% decays when a half-life is reached. And one half-life is 3.8 days, which is a known quantity for radon. So after 2 half-lives, 25% of the mass is left over, and that keeps halving, and therefore we can see that the half-life is constant. Dinitrogen pentoxide decomposes according to this reaction. Now use the data below to first determine the order of the reaction. Well, we can see that every 20 minutes, the concentration of the reactant gets halved. So therefore the half-life is constant, and this is true for a first order reaction. Now the average rate at which the reactant is consumed between 20 to 40 minutes can be obtained by taking the change in concentration on a change in time. Now the concentration of the reactant at 80 minutes can be obtained using the half-life. So effectively the concentration just keeps getting halved, which gives the following result. Now if the instantaneous rate is given at 30 minutes, what is the rate of appearance of nitrogen dioxide? Well, the rate of the reaction can be written using the stoichiometric coefficients. So if we make this substitution, and negative because the reactant is being consumed, we obtain the following rate of appearance of nitrogen dioxide. Elementary reactions are single-step reactions where the reactants are converted directly into products. And the first type is unimolecular, where a single molecule is rearranged and converted into a product or multiple products. So an example is radioactive decay. And using the stoichiometric coefficient of the reactant, the rate law is first order. Now a bimolecular elementary reaction is where 2 molecules collide to form products. And these can be the same or different molecules. So using the stoichiometric coefficients, so we can write the rate law as follows. And this second type of reaction is where we have 2 different molecules reacting. So the overall order of both reactions is 2. In termomolecular elementary reactions, 3 reactants collide simultaneously to form products, which is rare. And here are 3 types, where we use the stoichiometric coefficients to write the rate laws. So this type of elementary reaction is third order. For an elementary reaction to successfully produce products, the reactants must successfully collide to initiate the breaking and formation of bonds. Successful collisions must overcome the activation energy barrier, and the molecules must be oriented a certain way relative to each other. So here, for example, where carbon monoxide collides with oxygen, no reaction occurs, whereas if the carbon is facing the oxygen, you get the formation of a carbon dioxide molecule and an oxygen left over, which would bond with the other carbon monoxide molecule. Now using the Maxwell-Boltzmann distribution, which describes the distribution of particle energies, we can qualitatively estimate the fraction of collisions with sufficient energy that lead to a reaction. So here, for example, if we have a lower temperature, then there's a narrow distribution of gas particle energies, and only a small fraction are going to overcome the activation energy to initiate the reaction. Whereas for the higher temperature, and therefore there are likely more collisions that have sufficient energy to yield a reaction. The energy profile of a single step or elementary reaction gives the energy along the reaction coordinate, which is the axis along which the complex set of motions involved in rearranging reactants to form products can be plotted. And an example is the synthesis of carbon monoxide and oxygen to form carbon dioxide. Now here we start with the reactants, which have some energy, and every 2 carbon monoxide molecules react with oxygen. And at this stage, no bonds are broken or formed. Now if they have sufficient energy greater than the activation energy, which is the difference between the energy of the reactants and the energy at the transition state, and the molecules collide with the correct orientation, bonds are broken between the oxygens, and then the reaction proceeds to the products where the oxygens bond to the carbon monoxides to form CO2. And here the energy of the products is smaller than the energy of the reactants, so heat is given off to the environment, which is what we call an exothermic reaction. The Arrhenius equation is based on observations from collision theory and relates the temperature dependence of the rate of an elementary reaction to the activation energy required by molecular collisions to reach the transition state. And recalling the rate law was written in terms of the rate constant, and T is the absolute temperature in Kelvin. A is known as the pre-exponential factor, or number of collisions per second at the correct orientation of the molecules, and this is treated as a constant in the Arrhenius equation. Now EA is the activation energy, R is the universal gas constant, and this entire exponential term is the probability that a collision will result in a reaction. Now as the temperature increases, the rate constant increases, meaning that a higher temperature means that there's higher energy of the molecules and more collisions will take place. And if the activation energy increases, the rate constant decreases and the rate of reaction decreases, meaning that more energy is required to reach a transition state and less collisions will lead to a reaction. A reaction mechanism consists of a series of elementary reactions or steps that occur sequentially, and many reactions occur in a mechanism. So for example, nitrogen dioxide reacts with carbon monoxide to produce nitric oxide and carbon dioxide gas. Now if we sum these elementary reactions together, we obtain the following on the left hand side and the following result on the right hand side. And we can cancel out what appears on the left and right hand side, and therefore we obtain the following result. So summing the elementary steps gives the overall balanced equation. Now NO3 is a reaction intermediate because it's produced and consumed in the elementary steps, so it's only present while the reaction's occurring. And the experimental detection of a reaction intermediate is a common method to provide evidence that supports one reaction mechanism over another. So here, this reaction mechanism is preferred for this reaction. We can determine the rate law for a reaction from the reaction mechanism, and for this special case, where each elementary step is irreversible, or the first step is the rate limiting step, we can determine the rate law by the molecularity of the slowest elementary step, which is the rate limiting step. So this step may occur on the order of seconds, and the second step can take milliseconds to complete. And effectively the speed of the entire process cannot be faster than the speed of the slowest step. So for elementary reactions, we can use the stoichiometric coefficients of the reactants to determine the rate law. So for example, the reaction in the first step is bimolecular, and here this rate law is consistent with the one that's obtained from experiment. And experiments may involve measuring the initial rate of reaction, detection of intermediates, and so on. And because this is a multi-step reaction, the rate law is not simply equal to the rate constant multiplied by the concentration of each reactant raised to the stoichiometric coefficient. We can use the steady state approximation method to determine the rate law for a multi-step reaction where the rate determining step is not known. So first we'll assign a rate constant in the forward and backward reaction of step 1, and another rate constant for the irreversible reaction in step 2. And we'll write the rate law using the irreversible step, and because B is an intermediate, it's being produced and consumed in the elementary steps. This is not our final rate law. So using the steady state approximation, where the rate of change in concentration of B with respect to time is 0, or the rate at which B is consumed is equal to the rate at which it's produced. So in step 1, we can write the rate law for the forward reaction as follows, and in the backward reaction B is being consumed, and in the second step B is being consumed. And then if you do some algebra, and now we can substitute for the concentration of B in the rate law. So this here is a constant, so therefore we can write our final rate law, which is second order with respect to reactant A. The pre-equilibrium approximation can be used to determine the rate law for a reaction mechanism, where the first step is an equilibrium reaction and not the rate determining step. So first we assign rate constants for the forward and backward reaction and the irreversible reaction. And now we can write the rate law using the slow step. And B is an intermediate, so this is not our final rate law, which we need to write in terms of the reactants. So using the pre-equilibrium approximation, we assume that equilibrium is reached quite quickly, where the rate at which A is consumed in the forward reaction is equal to the rate at which B is consumed in the backward reaction. And now solving for the concentration of B and substituting this in our rate law, we obtain the following expression, and this here is just another constant, so we can write our final rate law for this reaction mechanism as follows, which is the same result that we got using the steady state approximation. We can construct the energy profile for a multi-step reaction by knowing the energetics of each elementary reaction in that mechanism. So we start with the energy of the reactants, and when the activation energy of step 1 is reached and the molecules collide with the correct orientation, for example, due to heat added to decompose the molecule AB into simpler molecules, then at transition state 1, the bonds between AB are being broken, and then after transition state 1, A and B are separated. Now when the activation energy of step 2 is reached and the molecules collide with the correct orientation, the intermediate B reacts with the reactant C, and then after this transition state we end up with the products. So in step 1, bonds were broken and heat was added to the system, so this step is endothermic, and in step 2, bonds were formed and heat was expelled to the environment, so this is an exothermic process. And overall, the energy of the reactants is higher than the energy of the products, so the overall reaction is exothermic. A catalyst can increase the rate of a reaction by increasing the number of effective collisions and also providing a reaction path with a lower activation energy. So for example, in this reaction, the catalyst is consumed in a rate-limiting step and regenerated in a subsequent step, whereas the intermediate Y is produced in the slow step. Now a typical example is the decomposition of hydrogen peroxide to form elephant toothpaste, which is a large foam-like substance, and this reaction is very slow. Now adding potassium iodide to a solution of hydrogen peroxide accelerates the reaction. So the iodide catalyst is consumed to increase the rate of reaction of the slow step and regenerated in a subsequent step. And here you can see that hypoiodite is the intermediate. So as we can see, the catalyst created a multi-step pathway that has a lower activation energy. And we can see that the addition of the catalyst did not change the energy of the reactants and products. And the net concentration of the catalyst in this reaction is constant. Some catalysts increase the rate of a reaction by binding to the reactants. An enzyme catalysis is a homogeneous process because the enzyme functions in the same phase as the reactants. And the reactants are called the substrate in a biological process. So enzymes are large biomolecules that have many functions within living organisms. Now an enzyme has an active site where the substrate is going to react with the enzyme through non-covalent interactions. And the enzyme substrate complex is the intermediate formed in the rate determining step. So the catalyst binds to the substrate to speed up this step. And the intermediate is consumed and the product is formed in a subsequent step. And this process keeps repeating many times in a biological environment or living organism. Now the enzyme causes the reactant to be oriented more favorably, such that the reactant molecule fits in the active site of the enzyme or large biomolecule. And this type of exposure provides a reaction pathway with a lower activation energy. Some catalysts involve covalent bonding between the catalyst and the reactants, where the reactant or intermediate either gains or loses a proton. And a prime example is the acid catalyzed hydration of ethylene. Now step 1 involves the protonation of the double bond in ethylene. So because hydrogen is significantly positively charged in the hydronium ion, then that creates a strong reaction between the hydrogen and the pi bond, where the electrons are used to create a bond between a carbon and hydrogen. And this yields the carbocation. And step 2 involves the formation of the oxonium cation, where the carbocation reacts with one of the lone pairs in the H2O molecule to form a bond between the carbon and oxygen atom. And step 3 involves the deprotonation of the oxonium cation to regenerate the hydronium ion. So here the catalyst is hydronium, which is consumed to speed up the rate limiting step. And it gets regenerated, and the carbocation and the oxonium cation are intermediates. Surface catalysis involves a reactant or intermediate that binds to a surface or forms a covalent bond with it. And that introduces new elementary reactions, and it's a heterogeneous type of catalysis where the reactants and catalysts are not in the same phase. So for example, in a catalytic converter of a car, you have a sheet of platinum that's used to oxidize harmful carbon monoxide into carbon dioxide gas. And step 1 in a reaction mechanism is adsorption, where the carbon monoxide and oxygen molecules are adsorbed onto the platinum surface, and this here is the slow step or rate limiting step. And step 2 involves the oxidation of carbon monoxide into carbon dioxide. So this is a possible reaction mechanism, where the platinum catalyst is consumed in the rate limiting step and regenerated in the subsequent step. And the intermediates are carbonyl platinum and platinum dioxide, which are produced in a rate limiting step and consumed in a subsequent step. Given the following 3-step reaction mechanism, write the equation for the overall reaction and label the catalysts and intermediates. So if we add the molecules on the left and right and cancel out those that appear on both sides, we obtain the following overall reaction. And here C and D are the intermediates because they're produced and then consumed in a subsequent step. And here there are no catalysts. Now write the rate law for the reaction, assuming step 2 is the slow step. So we can write the rate law as follows. And this is not our final rate law because C is an intermediate. So here we'll use the pre-equilibrium approximation because the first step is faster. And now we can solve for the concentration of the intermediate and then substitute this into the rate law. And this here is just another constant. Now in part C, we're asked to determine the units of the rate constant. So using dimensional analysis on the rate law, and then if we divide through by molar squared, the units of the rate constant are molar to the -2 by seconds to the -1.